Welcome to Advanced Math Unit 12, Part D, Page 3, Walkthrough. We've just had an example on page 2 where we looked at a vector formed from the coefficients of a linear equation in standard form, and we investigated whether that vector had a relationship to the line. And it turned out that that vector and the line were perpendicular to each other. And so the very top of this page is really restating this observation that if you have a linear equation in standard form, then a perpendicular vector, that is, a vector that's perpendicular to this line, could be created by forming it from the components a and b, where a and b come from the coefficients of the line itself. So we have this connection between a line and a vector such that these are perpendicular to each other. This is restating it. Now, question is, if you found one vector that's perpendicular to a particular line by forming the vector from those coefficients, is there a way to find additional vectors that are also perpendicular to that line? And another way to state that is, are there ways to find vectors that are parallel to this vector? Well, that means finding vectors that have two components that are proportional to the original components here. One way you can do that is to take your original vector AB and multiply it by any scalar. And a scalar, if you remember, is just a number. So if we had a vector 3, comma 5, those are its components, you could find a parallel vector by taking 3, comma 5 and multiplying those numbers by any single number. Um, so this is not rocket science by any means. Let's try an example. Example 3, find a vector parallel to u, whose components are 3, negative 2. So what we could do is say, well, one example would be 2 times vector u, which would be equal to 6, comma, negative 4. All I've done again is taken the components, 3, negative 2, multiplied them by 2. So this is a second vector. Sorry, this is a second vector, 6, negative 4, that's parallel to 3, negative 2. It's in the same direction as 3, negative 2, and it's twice as long. Parallel. Right? Another example. Find a vector parallel. Now we're going up to 3 dimensions. Vector v is 7, 1, negative 5. So it's perfectly reasonable. We just use similar technique. Let's try it again. Same idea. 2 times vector v will be those components multiplied by 2. So we'd have 14, comma 2, comma negative 10. So there's a second vector parallel. And I could choose negative numbers, and I could do negative 2, would work just as well. Now we're going to extend that idea a little bit. Now I've got equations for a line in both cases, and I want to find for each of these lines two vectors that are perpendicular to the line in component form. So when you've got something asking you for a perpendicular vector to a line in standard form, all you need to do is grab the a and the b coefficients and use them to form a vector. So the vector 10, comma 5 is perpendicular to that line. And to find a second one, I could just multiply it by 2. Or negative 1, or any scalar. Another example, same idea. Take the coefficients and put them into a vector in component form. And now I'll try multiplying this one by the scalar negative 1. So I'll get negative 33, comma, positive 7. So there's the second vector, same length as the first, opposite direction, but still parallel. All right. And same thing works for planes. Planes just like a line, except it has 3 dimensions instead of 2. So a vector that's perpendicular to the plane 2x minus 4y minus 2z equals 10. I just grab those coefficients and use them to construct a vector. This vector is perpendicular to that plane. I'm just grabbing those coefficients and forming a vector. Now, any other uh, vector that's a scalar multiple of that. So, for example, if I multiplied it by 1/2, I'd get 1 comma negative 2 comma negative 1. Now, that's another vector that is perpendicular to the plane equation given. There are an infinite number of perpendicular vectors possible just by changing the sign and magnitude of the scalar that I multiply by. So here's one. This is a little tricky. It looks sort of like in number 8, a linear equation, but it's got y and z. So really this is a plane equation. And I can see that by rewriting it with an x term. This would be 0x plus 5y minus 7z equals 22. So a vector that's perpendicular to that would be grab those coefficients and use them as components of a 3D vector. So it's 0, comma 5, comma negative 7. And then to find a second vector that's perpendicular to that plane, I could just try multiplying those by 2 or any other number. So it's still 0, then 10, negative 14. So again, an infinite number of possible vectors that would satisfy that. All right, next up we have, what is it? Page 4.